to turn it over to Al Texera now.
Thank you, Dan. Good morning, everyone. As Dan mentioned, we're going to go over PCSC technology. It's going to be an introduction. It hopefully will get you grounded in the basics of PCSC and enable you to go on your own and learn as you need to. And we're also going to go over lightly the ZXP-Series Card Printers. We're going to talk about how the SmartCard technology is supported by the printers and why it was implemented in the way that it has been implemented. Hopefully you'll find this talk very, very beneficial to you. Oops, sorry. Looks like my laptop seems to have locked up here. There we go. Okay. So we're going to be emphasizing introduction to PCSC technology, application integration, and how the card printers are wrapped into that to become a solution. Our agenda for today, we're going to start with an overview of the ZXP-Series Card Printers. Then we're going to go into the supported contactless SmartCard Technologies, the brief overview of both, and what we call the officially supported SmartCard reader. For PCSC, there's a particular reader, Zebra OEMs from a manufacturer. We'll talk briefly about that. And then we'll go into a high-level presentation of the SmartCard reader integration in the ZXP-Series Card Printers, explain how it's integrated into the printer and why it's been done that way. And finally, we'll start talking about PCSC. What is it? Why do we use it? Why do we emphasize it so much? An overview of the PCSC API. It will not be the complete API. We don't have time today. And then go through the basic usage. And this is introductory in nature. I'll be teaching you the basics of how to work with PCSC, and I'll be showing you specifically how to work with it within the context of using one specific smart card. Hopefully you'll find that information useful, and I've also got some very good resources and user group information in here, which I've personally found to be very beneficial as I've worked with PCSC. And then we'll have, I believe, a 10-minute presentation, 10 minutes of questions and answers, any discussions. All right, hopefully by the end of this presentation you will understand the following. What I just mentioned before, how the card printers are integrated to the SmartCard technology, why we do what we do, and how it came about. First we're going to talk ZXP-1 and ZXP-3. These are Zebra's entry-level card printers. They're command-based in that you send an individual command and individual data to the printer, so they are single-job printers. As you can see here, the configurations include single-side, dual-side printing, magnetic encoding, and PCSC SmartCard support. ZXP-3 is the only one of this family that actually has SmartCard support. ZXP-1 is a much more basic printer. So we're talking a little bit about ZXP-3 and our ZXP-7 and our ZXP-8. The high-end ZXP-7 is the direct-to-card printer. It also supports USB Ethernet. This one is job-based. This printer can support up to 3 jobs at a time. We generally talk about a job meaning what you need to do with the printer to produce a card, whether it's just printing and magnetic encoding, SmartCard encoding, SmartCard encoding and printing. This particular printer supports both PCSC and UHF. Those are the 2 main families of our SmartCard that we support. This presentation will not cover UHF. We do not have the time, unfortunately. The ZXP-8 is the high-end retransfer card printer. Just like the 7, it's a multi-job printer. It is job-based. You send an entire job to the printer, and it can handle 2 jobs or 2 cards simultaneously. And it only supports PCSC currently. Supported card technologies. For contact cards, there are 2 main types in PCSC. There's contactless. The contact falls under the ISO 7816 for asynchronous cards. That is an international standard. Among the things that it defines, the dimensions of placement of the contacts, you can see the picture there. You'll see the contacts, the gold printing is the contacts, the triangular shaped pads, the square pads, the rectangular pads, those are all electrical connections. That's power, ground, data stream, addressing, etc. Then below that you can see the circuitry. This is surface mount technology, and that this is on the outside of the card. You physically have to make a connection. The 3 card printers, when working with contact cards, there's actually a connection that's made as a set of pins that the printer will clamp down appropriately onto the pads to make the electrical circuit happen. Among the standards that are enforced by the 7816 are how to lock down on the card, locking down the card, that is security. How do you lock someone out of the card, how you open the card, read-write access, etc., and the overall program of the card. To be ISO 7816 compliant, that chip has to be placed in a specific place on the card, and the configuration of the electrical pads have to be a certain configuration. For the contactless, this is what we call proximity or near field. It's covered by ISO 14443. It's similar to its contact cousin in that it also defines the characteristics of the card, in this case, identification and transmission protocols for wireless connection. And that falls in among the things that are regulated by that are the radio frequency and power signal interface. The card here you're seeing that with the peeled back look that you see, that small chip on the bottom is the actual chip. That gold border running the perimeter of the card, that's the actual antenna. If any of you have ever had an employee badge, like many Zebra employees, we have to wand our badge at a sensor to walk in the building. That's the identity. That's proximity or near field. You have to be almost on top. Well, you actually do have to be on top of the sensor. You've got to be within an inch or two of the sensor. Those are the two main PCSC families. I mentioned UHF. I'm only going to mention it here briefly. I'm not going to talk anymore about UHF after this. This is long range or far field. ISO 18006C falls under what is known as the Gen 2 Air Interface Protocol. That is the interface. That's the protocol that Zebra uses. It's been widely adopted in many industries. If you look to the right where the card is, where they're peeling back the card, that large X you see, that's actually the antenna. That allows the card to transmit up to 50 feet away from the sensor. That's what we call long range or far field. It also has very high speed chip acquisition. That particular X pattern you see there, that is patented technology. Zebra actually modeled and developed that particular antenna. No one else can use it without licensing it from Zebra. Supported card technology, the PCSG reader. That picture gives you, that's not the actual reader that's in the printer. The one that's been in the printer I was unable to find a picture for, but this is its cousin, it's the next generation up. But it gives you an idea of what the reader looks like in the printer. It's just a simple little circuit board that's interfaced to the motherboard of the printer. It's fully PCSC compliant. When we get into PCSC, you'll understand a little bit more about that. It also has various operating system compatible device drivers covering, I believe, from Windows XP all the way through Windows 10. It has the manufacturer also has device drivers for Linux, Unix, and even the Mac OS. So it's a really well-adopted card. We've been using it for quite a long time. This particular reader is dual purpose. It has both a contact and contactless reader built into it. It saves us a lot of room in the card printer, and it's convenient for the customer. It allows the customer to switch easily between the two. This is the high-level schematic of how the SmartCard module is actually interfaced into the printer. You see there the Adentive SDI101, that's the reader. You notice in the schematic it's wired directly to the USB port, as is interfacing to the printer firmware. You notice on the outside of that schematic I have a line that says direct access to via USB port. Two things come in through that USB port. First of all, it's programming access to the printer itself if you're doing printing, mag encoding, what have you. More importantly for this presentation, it's how you access the SmartCard reader. We actually give the customer direct access to the SmartCard reader in the printer. The reason that we do this is without that direct wired, we would not be able to use PCSC. Doing this has quite a few advantages to us, as we'll get into a little bit later in the presentation. But understand what the schematic is emphasizing is that for the ZXP-Series printers, the 3, 7, and 8, the printer itself is not involved in any of the SmartCard encoding whatsoever. That is done directly from the customer's application, right on through, straight in through USB to the SmartCard reader. How do we support SmartCard encoding in the ZXP-Series printers? At a high level, what happens is the following. When a job is received by the printer that is for SmartCard encoding, the printer draws a card either from the hopper or it pulls the card in from the ATM slot. The card is positioned at the contact or contactless station, depending on the type of card it's using, and then at that point, the printer sets up the card to be encoded. If it's a contact card, it will clamp down on the chip, make the electrical circuit, and then it reports that the card's in place. If it's contactless, it will energize the RF field necessary to carry the wireless signals, and then again, it will signal the application. In this case, it could be one that you've written, our customer's written, what have you. It signals the application that the card is now positioned and the printer's been ready to be encoded. At this point, the printer just sits passively. It waits for further instructions. It's at this moment that the customer's application would then have access to that card through that USB port that I mentioned back here earlier. Once the card's in position, you now have access to the card, do whatever you need to do with that card, whether it's read, write to it, encode it, validate it, whatever you're going to do. The ZXP-Series printers were a little bit different than the legacy printers for Zebra in that these were designed to be passive devices with respect to SmartCard encoding. Because the printer plays no part in the encoding of the card, its sole responsibility is to position the card for encoding and then go into pause mode. If it's the ZXP-3, it'll wait for the next command. If it's the ZXP-7 and 8, because those are job-based, it already has an entire job that it knows what to do. What you do at the end of the SmartCard encoding is you simply send a resume or cancel command, depending on whether the card was successfully encoded or was not. In both cases, the printer is just simply sitting in passive mode. It's waiting to be told what it needs to do next. It has no idea when the SmartCard encoding begins, nor when it ends. It's just waiting for the developer at the right time, or I should say the application at the right time, to then tell it, eject the card, something went wrong, or continue on, do the printing, etc. The reason that we do this, and the reason the SmartCard reader is wired directly to USB port, is that currently there are about 1,300 different smart cards on the market. In Q4 of 2012, 300 new smart cards came onto the market. With that explosion in smart card technology and the level of sophistication each of these cards has, there's no way that Zebra could keep up with all those cards. If we expected the printer to do the smart card encoding, which was done in the legacy printers, which are now discontinued, we would have to literally know up to 1,300 cards to guarantee support for the market. We simply don't have the resources for that. When the ZXP-Series printers were designed, they were designed to be agnostic with respect to the SmartCard card, the SmartCard technology. So it was chosen, so the idea was that we would move the card into position, and then using PCSC, which is an industry standard SDK, which we'll talk about momentarily, it allows the printers and it allows customers to access literally any PCSC compliant smart card. It relieves us of the responsibility of knowing what that card may need, may not need, and it relieves us of having to support each and every different card that may be on the market. It was actually a very smart move on Zebra's part to do this, and it allows us a maximum market coverage of the SmartCard technology. So why did we go with PCSC? In 1998, a company called the PCSC Work Group developed what became the PCSC standard. It's an SDK, it is a third-party industry standard. It has become the de facto standard for smart card encoding. You'll find outside the United States, it's widely adopted in many different industries. As we get into it, you'll understand why. It's a very simple but very straightforward protocol to work with. It's available in every flavor of Windows, starting with Windows XP all the way through to Windows 10. There are implementations of it now for Linux and Unix, and there's even what they call a forked version of PCSC for the Mac OS. What it allows you to do with PCSC is a standard way of working with any smart card. Manufacturers of smart cards have to comply with this standard. They support it. Regardless of what their security attributes are for the card, the communication path to the card is this particular communication specification. Because of the substantial market availability of smart cards that support the PCSC standard, it made sense for Zebra to follow that as well, rather than trying to spin its own version of an SDK, and then we'd be in a constant cycle of updating the SDK every time a smart card came out. And with 301 quarter alone, that would be overwhelming. The amount of resources it would take both on the engineering side to maintain that, and on the business side, marketing it would take to figure out which smart cards are about to come on the market, which ones are now obsolete, which ones have fallen out of favor, which ones are being replaced with which. The amount of resources to maintain that are just not practical. Instead, using the PCSC interface, which is what we found in Europe and Latin America, and in APAC, Asia Pacific, it's so widely adopted, customers are actually upset with Zebra originally with the legacy printers for not having done this in the first place. PCSC overview. These are the functions that we're going to use. There's about 12 or 14 functions total that make up the PCSC SDK. These are the ones I'm going to work with today. These are the most basic ones. The reason I chose these 6 is just about every smart card on the market you will use these 6 with. The other ones are a little bit more advanced. You may or may not need them. If you master these and know how to work with these, there's just about no smart card, PCSC smart card I should say, on the market that you would not be able to work with. The first one is how to get a handle to the SmartCard SDK itself. The second one will release the handle when we're done. S-Card Connect opens a connection to the SmartCard reader, and we'll see why that's significant in a moment, and closing connection to the reader. We actually open and close connections to the SmartCard reader, not the SmartCard itself. S-Card Status returns various information about the card, and it's fundamental. That one is fundamental to knowing whether or not your card is PCSC compliant. I'll show you in a little bit what I mean by that. And S-Card Transmit. That one is the heart and soul of the communication with the card. That is the transport mechanism that sends the commands to the card and retrieves information from the card. And I have sample code that will show all of this. Overview. The transport APDUs are the heart and soul of how PCSC works with a smart card reader and a card. The APDU stands for Application Protocol Data Unit. The official definition is a communication unit between a smart card reader and a smart card. Those of you that have ever done any programming with communication protocols, you know about building packets. You have data packets, you have addressing, you have payloads, etc., etc. The APDU is nothing more than how you build a command and the associated data that command requires, and then send it on to the smart card. In this case, we're going to deliver it to the smart card reader, and the reader is going to be responsible for passing it on to the card. There are two categories of APDUs, command and response. That is how PCSC works. We, as developers in our application, we build command APDUs. We deliver those to the reader. The reader then forwards them onto the smart card. The smart card sends back response APDUs. The response APDUs tell us whether or not the card was able to carry out the command we asked it to, if there were any issues with it, any errors, etc., etc. All the APDUs are developed by the manufacturers for the card. You look at the manufacturing specification, both the smart card and the smart card reader, as how to build the APDU. The basic command structure for an APDU is such that you have 5 packet header. You have a 5-byte header. The first one sometimes is called CLA. It stands for the class of the instruction. These are manufacturing specific. All we care about is that we comply with it. The second byte is the instruction, the actual instruction code. What are we asking the card to do? Is it reading? Is it writing? Is it locking down a particular area of a card, etc., etc.? Then parameter 1 and parameter 2. Some of the PCSC command structures have additional parameters that accompany them. That was what those 2 parameters are for. The next one is your payload, the length of the command. If the particular command requires additional data, this is where we specify the length in bytes for that command. Then the following is the command packet itself. If there's any data that would have to go with the command. The most common would be a write command. We're ordering the card to write data into a particular location in the card, so the command data would be that data we're writing into the card. If this sounds a little hazy for you at the moment, don't worry. We're going to see this. We're going to come back to this in code in a little bit, and you'll see over and over how this works. The final packet is a length of, it's called the encoding the maximum number of response bytes. There are some new cards that are very sophisticated in security, and there's a lot more handshaking, a lot more security that goes on with it. This particular portion of the command APD would be where you define that information, where you tell the card how much data you want read back, different types of handshaking, the amount of exchanges that have to take place to authenticate a card. This particular packet we're not going to talk about in this presentation. It's more advanced. We are going to follow the first 5, what I call the classic PCSC command APD structure. This is what we build, by the way, as developers. We're going to be sending this to the card. The response APDUs we get back from the smart card itself. If there's data associated with the response, we get the data ahead of this we call the status 1 and status 2 bytes. Status 1 and status 2 bytes tell us whether or not the command worked or failed. For PCSC, they define 90 hex and 0 as successful command compliance. If something we asked the card to do worked and the card believes it did the action correctly, the status bytes will be 90 hex and 0. You can consult the appropriate manufacturing documentation for actual error codes. If there's any data that comes back that will precede that, the most common is when we do a read. If we're reading data out of the card, that is the most common for the response data. An overview of how the command APDU and receive APDUs work. As card transmit, as I mentioned earlier, is the PCSC transport mechanism. That's the function that's going to do it. At a high level, as I mentioned previously, we build the command APDU and we send it through PCSC to the smart card reader. Upon receiving it, the smart card reader will extract that command APDU and it would forward it on to the card. So the reader actually is what is communicating with the card, not our application. The card carries out whatever that command was. It assigns appropriate status bytes as to say whether it failed or it succeeded, and it returns that back to the smart card reader. The smart card reader then packages up that response APDU and forwards it back to our application. SCARD transmit, like all PCSC functions, are blocking calls. When that function returns, we should now have an APDU response from the card, which we'll evaluate. At a high level, PCSC boils down to we build the command APU and we send it through PCSC, in this case the SCARD transmit function, to the reader. We're always building, sending command APDUs, and we're always evaluating response APDUs. When you master that, there's virtually no smart card that you can't work with in the PCSC world. A little bit lower level looking at this, what I call the application integration stack. Our application is building and sending the command APUs. WinSCARD DLL is the actual DLL in the Microsoft Windows world that houses the PCSC API. It is available to, as I said before, starting with Windows XP all the way up through Windows 10. It is available to you for free. Microsoft gives that away to you. Through the SCARD transmit function at the operating system level, we deliver the command APU to SmartCard reader. At that point, the reader strips out the command APDUs, sends them onto the card carries out the command, sends back the response APDU, builds and sends it back to the reader. The reader packages that back up in the SCARD transmit function and returns it back to our application. So at a high level I mentioned before, I'm going to keep coming back to this over and over because this seems to be where a lot of confusion is when we have even internal resources as well as customers about how to use PCSC. Building and sending command APUs and evaluating the response APUs. All the sample code you're going to see that I'm going to demonstrate momentarily follows this paradigm. We're going to be working specifically with the Mikare 1K card. This came right out of the manufacturer's specification for it. This is the memory map for the card. You'll notice that there are 16 sectors ranging from 0 to 15. Each sector has 4 data blocks, not 4 blocks I should say. The first sector, sector 0, in block 0 is the only special purpose one. They've noticed it's called the manufacturer's block. If you go in there with a read command from PCSC, one of the things you can extract is the serial number of the card. They normally call it the UID or universal ID of the card. Think of it as the serial number of the card, uniquely identifies the card. Other information that's in that particular manufacturing block is the lot that card was manufactured with, the date of manufacture, and even actually the manufacturer of the card. Each manufacturer has a special code that they embed in there, so you can tell which manufacturer actually produced that particular card. You notice from the footprints, you'll see that in sector 0 there are 2 data blocks. That's general purpose. That's where we're writing our special purpose information into the card. And the sector trailers is block 3 in each sector. That one is the security configuration. There are 2 keys, or up to 2 keys I should say. Those keys are how you deny and grant access to that particular location on the card. Access bits, how you set up the security for the card. Among the things you can do with access bits, I can decide at a sector level if that particular sector has only read access. I don't allow writing to go onto that card once the card's been programmed. I can set it up for write only. I may only want to have write access into that particular sector because I may be doing something like metering. A good example of that would be ski lift tickets. We have some of our customers are ski lift operators. So if you've purchased ski lift tickets and they're going more electronic than paper anymore, you may have a section of this card that's been set up with the number of lift tickets that you currently have, and as you pass through a sensor, that particular counter is dinged. So that would be an example of a write only. Read only would be maybe information about, is your membership currently active, who are you, etc., etc. With the access bits, I can write those, then I can lock them down read or write. I can also lock down which key is needed on a sector by sector basis. I can say, well, for sector 0, I want key A to be the active key. I may have key B in there just as a way of thwarting any hacking. They may not know which key is active. I may want key B to be the active one in that sector. I can even lock it down as far as if I'm doing a read operation, I can determine dictate which key should be the active key for read and write operations. Each one of these keys is unique to the sector that it's defined in. So you'll notice we can have up to 32 different keys. We can have up to 16 unique key A's and 16 unique key B's. And you may want to do that with your security strategy. That way, if somebody hacks into your card, for some reason they find a key, they're only getting a partial hack. They may only have access to one sector, or in case half of a sector, depending on what you're doing. This memory map becomes important as we go through this code because what we're going to do is I'm going to demonstrate how to go into sector 0, block 1, write data into that location, and then read the data back out to verify that the write actually worked. Here's our first example of real APDUs. This came right from the SmartCard reader manufacturer. Read binary blocks. Notice the 5-byte header that I mentioned before. We're looking at the class of the function. In this particular manufacturer, it sets up the class. They're all FF hex 255. The instruction is the key here, what we want to carry out. For a read operation, it's going to be B0, P1, and P2. In this particular case that I'm talking about, the MyFair 1K card, dictate the sector and the block. How we instruct the card with respect to which block in the memory that we want to access. And you'll notice that P1 is hard-coded to 0. The reason that is, going back to the memory map for a moment, this particular smart card manufacturer didn't want to deal with sectors and blocks. So in their implementation of PCSC to support this card, they ended up doing a flat memory model. So instead of using sectors, they just use blocks. There are 16 sectors, 4 blocks per sector, 64 total blocks. You access each block by the range 0 to 63. So 0 would get us into the manufacturer block, 63 would get us into sector 15, block 3 for the sector trailer, that final block. That's going to become important as we start working with these APDUs. Same thing with the update. Let me go down briefly to show you the read binary block response format. You know it says N+2. Because we expect data back from a read operation, this particular card, the MyFair 1K card, we write in a maximum of 16 bytes of data. We get back 16 bytes of data. So for every read operation, our response APDU, if it's successful, should be 18 bytes in length. The 2-byte status to let us know if it worked or not, and the actual data that we require. Below that format, you see the response codes, and you see the 90-0, the 90 hex 0. Again, that's standard PCSC. Everybody follows that format, regardless of manufacturer smart card reader or smart card itself. The error codes are manufacturing specific. In this case, it just says 63, operation failed. You'll find most of the error codes in PCSC are vague like this. It's an anti-hack mechanism. The more we give detailed error codes, or I should say the more they give detailed error codes, the easier it is for a hacker to figure out if they're getting warmer, if they're actually getting into the card. If no matter what they do, everything comes back as just a generic 63 error code, it makes it very difficult for a hacker to make any grounds with that particular card. And you'll find that throughout manufacturers of the cards and the smart card readers. The error codes are deliberately vague. Update binary blocks. That is actually for writing data into the block. For whatever reason, they define it as update. I just treat it as a write. The instruction is D6. You can see the class is still FF. P1, P2 are sector and block. And again, we're going to hard code the sector to 0. And we're going to use block 0 to 63. In this case, it would actually be 1 through 63, since manufacturing block 0 is by default a read-only block. And then the final one is our data in block, which is where we're actually going to pick the data. How did I know it was 16 bytes from MyFair card? If you look down below where it's talking about the block number and it shows number of blocks to update, 16 bytes from MyFair 1K and 4K card. The 4K card is very similar in memory footprint to the one I showed you for the 1K, just 4 times as large. There's a little bit more, but it's beyond this scope. Then 4 bytes for the ultralight card. The ultralight is a very small footprint from memory. It's a very, very light card, so it's MyFair ultralight. The one nice thing about this is you'll notice that both of these commands, by definition, work for the 1K, 4K, and ultralight cards. So all the code that you're going to see demonstrated would literally work for all 3 of these cards if we were working with all of them. You can see the response code is, again, 90 hex and 0, and 63. Same error code. They're thwarting the hackers by giving them just one error code. These are the command APDUs we're going to demonstrate later on how to actually build to do the read operation and the write operation. The next one is the load authentication keys. Mentioned before, go back real quick just to refresh your memory, key A and key B. Before we can be granted access to the card, and this is for all 3 of these cards again, 1K, 4K, ultralight, we have to load a security key into the reader, not into the card, we're loading into the smart card reader itself. This is the command that does it. We tell it what type of card, we tell it what type of key it is, and we give it the key. In this particular manufacturer smart card reader, we can only load the key in volatile memory. There are some smart card readers where you can actually load the keys into persistent memory. This one is volatile. Excuse me. And the same 5-byte structure. You're going to see this over and over and over. The class of the instruction itself, and then the parameters P1, P2, the length of the command, and the data in. Very consistent protocol, very well done. Key structure, in this case, it's always going to be 0 because we can only write it into volatile memory. And the key number, we're going to be using 0 as well. They call it key number, but it's actually the parameter that defines where the key is located. What we're doing is we're instructing the card where to find the key for the validation. We're going to store it in the volatile memory of the reader, and then we're going to order the card to do an authentication. It's going to take over. It's going to pull that key out. It's going to compare that key with the key type, is it A or B, and the key value for the particular sector. In this case, for the particular block we actually want to gain access to. Final thing here is the 6 bytes. You notice it's showing 6 bytes of FF. That is the default key value for all cards when they're manufactured. Doesn't matter whether they're contactless or contact cards. If you get a PCSC card from a manufacturer, it's shipped to you in an unlocked and completely unlocked format. This is the default key that all manufacturers put into the card so we can access it. Part of our strategy, of course, would be to change that key either on a sector-by-sector basis, depending on what our security requirements are. We're going to load the key into memory. The next thing we're going to do, you have the same thing here with the status 1 and status 2 bytes. When we load the key, did it work? Did we get the key successfully written into the SmartCard reader? If we do, we've got a 90 hex and 0. If not, 63 error code. Notice again, just one error code, anti-hacking mechanism. Down below you see an example of an actual APDU. We would build this APDU and we would send it through PCSC to store that key in the SmartCard reader. The final APDU we're going to work with is the authentication. This is when we actually ask the card to authenticate us, to grant us or deny us access to a particular place in the card. Again, the class is FF. This time 88 hex is the instruction. P1 and P2, they follow the same format as the read and write. We're talking about blocks. We're going to authenticate on a block. Block by block, we'll authenticate to be granted access to do read and write. Or in the case of block 3, the sector trailer, you want to have permission to write a key in or read a key out and lock down the access bits, define what our security is going to be for that sector. Block number, block key type. Down below, if you look, you'll notice the key type. 60 hex is key A, 61 is key B. Everything we're doing here today will be 60, key type A. Below key number, we're always going to use 0 because the only place we can store the key is in volatile memory in the SmartCard reader. And then finally, the status response. Again, we're looking for 90 hex, and you'll see it's just a vague 63 operation error. So if a hacker's playing around on the card, all they're ever going to get back is 63 as an error code. It's going to be very difficult for them to know if they're making headway into that card, and that's by design. Those are the 4 APDUs we're going to use. Now the overview of how we actually pull these things together. Our goal is to write 16 bytes of data into my fair card and then read it and verify, and then read back the value to verify the operation. Here are the steps to do it. We obtain a handle to the PCSC SDK API. That's to the S-card established context. Once we have that handle, we have access to the SmartCard SDK, Then we're going to open a connection to the SmartCard reader. We're going to obtain a handle to the reader using S-card Connect. The next step using S-card status is to perform what's known as an ATR, or answer to reset. Every single card that is PCSC compliant must respond to the answer to reset. This is how you tell if your card is PCSC. If you're ever in doubt, you simply open a connection to the reader, you position the card obviously in the reader, or even a handheld reader if you have a handheld device. If the card answers to reset, you have by definition a PCSC compliant card. And this is how we help customers figure out if the cards they have are PCSC compliant. The next status we're going to do is we're going to load the key into the SmartCard reader using the transmit protocol. Then we're going to perform the necessary authentication. We're going to be given access to block 1. We're going to follow that with a write operation. We're going to write the data into the card. And then finally, we're going to read the data back from the card and make sure that the data was actually written into the card correctly. We'll close the connection and we'll return the handle when we're done. At a high level, this is what you do regardless of what PCSC card you're ever going to work with. These are the steps you're always going to follow. Now, depending on the security that you're doing, you may have to repeatedly load a key and perform an authentication. You will always have to, with a MyFair 1K card, you'll always have to perform an authentication because you're only granted access block by block. So if I want to go to block 2, 3, 4, what have you, I have to authenticate first and then I can read or write. If you have different keys, as I mentioned in the footprint, you can have up to 32 different keys for the different sectors. You would have to continuously continuously load the appropriate key, A or B, for the operation you want to do before you do the authentication. So it makes it very sophisticated. You can see, even though this card, by today's standards, would be considered a low-level security card, it still has quite a bit of security involved in it. And this particular card is considered obsolete now. There are other cards that are in the Mikare family that are much more sophisticated and a lot more memory. Just the demands of the market. Okay, basic usage. Now we're going to take a look at our first code. This is all C# code, by the way, so hopefully some of you have some experience with it. We're going to obtain the handle with the PCSC. First thing you see is DLL import, and you see the calling out the WinS card DLL. This is known in .NET as platform invoke. When we have a non.NET written DLL, such as this particular one, PCSC, it's a C-based, it's a C language DLL. To access it from the .NET world, we have to import it. If any of you did anything with VB6 in the past, that's very similar to declaring a function or a subroutine. DLL import gives us access to DLL. Then we model the function that we want. It's always going to be static extern. It can be public or private depending on your requirements. Here I've done it as public. It's always a static function, and it's the extern because that's the call to let the compiler, the .NET compiler, know that that function is external to your application. And the DLL import tells it where to find it. Don't worry about the parameters at the moment. We'll talk about those in a moment here. The code below that, we're going to actually get our context handle. In .NET world, we like to use int pointers instead of handles. If any of you did any classic C++ programming with Windows, you probably have used handles. Same context. The nice thing about the int pointer is it's platform dependent. It abstracts away 32-bit and 64-bit platforms in the Windows world. It'll size itself accordingly, so you don't have to worry about byte array, you don't have to worry about byte alignment, etc., etc. The code in blue bold is our first call. Once we've done our DLL import, we now have access to that function. We can use it as easily as any other function we've written in our code. The WinS card function describes different types of access to the card. Whenever working at the application level, it's always going to be, the scope will always be user. So you'll see the SmartCard scope user will be used for this repeatedly. Excuse me. The next two parameters, Microsoft reserves those, so we simply pass in null pointers. In this case, in pointer 0. More importantly, we're passing in our handle to our context. That's what's going to get populated with the handle to the SDK. Excuse me. Finally, I look to see return of non-zero. Just like most of Microsoft's programming paradigm, they like to return 0 for success. So we're looking for non-zero if it failed, and we're looking for a non-null pointer. I've personally never seen this function fail. I've seen the others fail, but I've never seen this ever fail. We have our handle to the SDK. Now we have access to PCSC. Next thing we need to do is open a connection to the SmartCard reader. Okay, same idea, DLL import. We have to bring that in. We have to bring in the S-Card Connect. By the way, if you've never seen this before, don't worry. We have sample code that demonstrates this. And all the code, I should say, that I'm showing you here today was taken from a QA tool that we have. I massaged it for the presentation, but this is actual working code in a QA tool that we work with. So now we're going to get our reader, we're going to get our handle to our reader. You use the Windows enumerated name. Identiv reader would not be the enumerated name. You'll get that from if you've ever gone into your devices and services, you'll find it there. There is a PCSC function for returning the reader name. It's outside the scope of this presentation today. Excuse me. And our call to S-Card Connect. We pass in the context handle that we got from the previous call, the reader name, and now the next thing is we're going to use shared mode. We always at the application level working with shared mode. Scope, user scope for establishing the context, getting the handle to the API. Shared mode when we want to actually talk to the SmartCard reader. The next parameter is the protocol we want to use. We use T0 or T1. There's also raw and something else, but for PCSC with classification we work with, we always use T01. Here they're ordered together because we're requesting either one from the reader. The reader is set up for one of those. We're letting the reader know we can work with either one. And we let the reader decide. If we're granted access to the SmartCard reader, the card handle will be populated with a handle to the reader, and the active protocol, that is it T0 or T1, that will be populated with the appropriate protocol. We will need the card handle and the active protocol for the other PCSC functions that we're going to work with. Just like I did for established context, we're going to look to make sure that the function returns successfully and that we actually have a handle. Next part, opening. We're going to obtain the card's answer to reset. This one's a little bit trickier only because I found with .NET I had to do a little bit of marshaling, and that's why you'll see the actual function imported, but you'll see below I call it a wrapper function. This is where I'm wrapping that function call. I had some problems with some of the ATRs or some of the cards if I used the SCard status function directly from .NET. So I wrote a wrapper function around it, and I did some marshaling, and I'm going to show you that code. If you don't know, if you haven't heard the term marshaling before, it's a technique that .NET provides, Microsoft.NET provides, to allow you to work with unmanaged memory. In this case, what I'm doing here is I'm actually creating a byte array with unmanaged memory. I'm stepping out of the .NET managed world. .NET, like Java Virtual Machine, is a managed memory map. You don't have to worry about resource leaks, memory leaks, etc. But in this particular case, if you need to go outside that environment and go out to the actual memory of the operating system, this is how you do it. You notice what I'm doing? The first function called, pay attention to only the stuff that is bolded, because that's the key. But this is literally the entire function of my wrapper function. I'm marshaling, I'm asking for the size. First of all, I have to find out what the size of the memory that I need. So I look at the native size of the byte that's represented in .NET, and then multiply it by the length of that array to get the size I need, the number of bytes I'm going to need. Then I go out and on the global heap, I allocate the memory. This is like the old style of new, when you did C++ coding, we're going out and we're getting unmanaged memory, which means we have a responsibility to return that memory when we're done, or we will leak memory. Now I have an unmanaged array. I have actually a pointer to an unmanaged array of bytes. But the next thing is where I copy. If this were a function where I had data in the managed array, the ATR array, that I needed transferred, this is where I would copy that content into the unmanaged array prior to transfer. In this case, in the .NET world, like Java, when I allocate an array in .NET, it automatically initializes the array to all zeros. So all I'm doing is I'm using this copy function to initialize the unmanaged array to zeros. Because just like the C++, whatever happened to be in that memory location when you were allocated that block of memory, that's what's in there. I want the array initialized to a known state. All I'm doing there in that situation. But more generically, this is how you transfer data between a managed and an unmanaged array if you needed to do that in your application. Now, from my wrapper function, now I call PCSC, and I pass it the unmanaged array. The unmanaged array will be populated with the ATR from that card if this function succeeds. Below that, the very next line of code is where I copy the contents from the unmanaged array into the managed array. This should be our ATR from the 1K card. You'll notice I'm not looking to see if that function call succeeded or not. At this point, I don't care. I want to get whatever the contents are, I'll worry about it later. Right now, I just want to get the function done, I want to get the data. And in the finally block, this is where we release memory. We're going to be responsible developers today, we're not going to leave memory hanging. So now we release the memory that we allocated. And again, this is outside .NET. This is the old style memory allocation. Now I'm going to show, now in the context of PCSC, you'll notice here's how I actually make that call. SCard status EX. I allocate my array for the ATR, I set up my protocol, and I get my reader name. When I make that function call, now I'm worried. Now I look at whether it succeeded or not. This is where I care about it. More importantly, down below, those hex values, those hexadecimal values, that's the ATR. If the card is PCSC compliant and the Mikare 1K card is PCSC compliant, this is what you're going to see. This lets us know beyond all doubt that this card is PCSC compliant. The nice thing about the ATR among that is that every type of smart card has a unique ATR. All 1K Mikare cards identify themselves this way. A 4K would have a different identification, ultralight, different contact cards. This is important if you don't know what card is in the reader. You can use the ATR to define it. You can, identify it if you happen to know what the ATRs happen to be. If you're working on multiple cards, different types of smart cards, you want to do this to confirm that the card you're going to encode is actually the card that's in the reader. Before I go on from this, I'll also tell you this one here, SCard status, this is the only PCSC function I've ever had to do marshaling with. All the others I've been able to do straight calls into the card through the PCSC mechanism. I should back up and tell you one other thing. I just got a little ahead of myself here. Getting a handle for the reader, getting a handle to the SDK, the reader, and conforming the ATR, you notice at no point did I do anything about the card itself. I didn't care about command APUs. I didn't care what type of card I was using. That's very important. That is standard PCSC. Every smart card, as I mentioned before, has to follow that format. When you get that hexadecimal value back, you know you have a PCSC compliant card. Now the next part, we have to load a key into the smart card reader. We're going to use our S-card transmit function. Here's our first command APDU. Key type is 60, as I mentioned before. The length is 6. There's the default factory set key. Now we're going to build our command APU. First thing we're going to do is we're going to set up the APDU, the first 5 bytes, setting up the command we want. The CLA or claw function, FF. The instruction itself, 82, which is to load the key. 0 defining as the reader's volatile memory, so the card knows where to find the key type. In this case, it's key A, and the key length, 6 bytes. Now we're going to complete the command APU. We're going to copy over the command data because this card requires command data. In this case, key value, 6-byte key value. We're going to build our response APDU buffer so we can get the value back from the card. And below that, we have what's called the protocol structure. There's a structure in Microsoft that Microsoft requires for its PCSC compliance. It's just 2 values in the structure. The protocol it's using, I mentioned we had the active protocol, and the PCI length. Currently it's 8. In the future implementation of Microsoft's Windows, it may change, but everything is 8 currently and the active protocol. This is what I call bookkeeping. It's PCSC bookkeeping for Microsoft's I/O response. We have our command APU. We've set up our response APU. Now we have the I/O request. Now we actually call it. S-card transmit. We pass the handle, the I/O, more importantly the command APU. And we pass in a buffer for the response APU, placeholders for that and the length. When that function comes back, we're going to look at the function return value, make sure that at the operating system level nothing went wrong, it completed. Now we're going to look at the length of the APDU. We load the card. You probably don't remember this, but from the manufacturer's spec it said it would be a 2-byte response, just the response of 90 and 0 for the status. You notice if I look for the length, then I look at the APDU response. I'm looking for 90 hex and 0. If that works, I know we loaded the key properly into the reader. Next step is perform the authentication. Again, using the S-card transmit. Now we're going to build our second command APU. 60 hex because it's the key type we're using, location of where the card is, or where the key is, volatile memory. We're going to build our command APU. There are 5 bytes for the instruction. The class of the instruction, the actual instruction, this kind, parameter 1 and 2 were not needed, and the length of the command, 5 bytes. Finished, we do what I call completing the command APU. The command data, in this case the key value, the information for the key, version number. This particular manufacturer requires the first byte to be 1. It's also in the spec. I think I glossed over it, my apologies. 0 hard-coded as per the vendor specification because we're not using sectors. 1 is the block. Which block in the card do we want to validate, we want access to? And then the key type that we're going to use, and where to find the key. So the smart card reader understands with key A, the key number, in this case the location, and which block we're asking for access to. We build a response APDU just like we did for the load key. You can start to see the consistency of the command APDU versus response APDU. We build our required Microsoft bookkeeping for the I/O transport, passing the active protocol. We call the function just like we did before. Same function, S-card transmit. Same parameters except for the command APDU. The command APDU is the only thing we're changing because we're sending a different command into the card. But our evaluation is the same. Did the function succeed or fail? Did we get back a 2-byte response? If we did, is it 90 and 0? Did the authentication work? In this case, since we sent the authentication over, if we get 90 and 0, we now have been granted access to block 1 in the MyFair card. Now we can do a read and write operation. Next part, going to write the 16 bytes of data. There's our 16 bytes of data, our super secret data ranging from 0 to F. Data size this time is 16. We're building our command APU. Notice we set up the command APU again, the same idea. Class of the instruction, hard-coded P1 because we're not using sectors. Second parameter, P2, is the block number. We want to write to block 1. We've been authenticated for it. And now the data size for the length of the command, in this case 16. Now we complete the APDU. Command data again. In this case, it's 16 bytes of data that's being written into the card. We create our buffer for the response APDU. We create our required I/O bookkeeping from Microsoft with the active protocol. And now we call S-card transmit again. The only thing that changed here is the command APDU, and the response APDU should be the same. So hopefully you're starting to see the consistency with PCSC. I said you build a command, you evaluate a response, you're seeing that's exactly what we're doing. And by changing the command APDU, we can pretty much do anything we want with the cards. Evaluating the function, looking for the 2-byte response, and evaluating the 2-byte response for 90 hex and 0. That worked. The write operation just succeeded. Now, if I'm bringing back the memory up map just to refresh your memory a bit, sector 0, block 1, where it says data just above the manufacturing block, that's what we wrote the data into, and we're going to read that back. S-card transmit is going to be used again. We're going to build our command APDU again. Class of instruction, the instruction itself, sector 0, hard-coded as per the manufacturing spec, block 1. We're going to read the data from block 1. The length of the command is 0. For the read, there's no additional data for the read command. We just have to issue the command. So we're going to complete. So we've completed our command APDU at that point with just the header information. We build our buffer for the response APDU. We build up our proper I/O bookkeeping again for Microsoft to make Microsoft happy, and we call the S-card transmit. So it's the same parameters. The only thing that's different is in the command APDU we sent over. This is when you know you're working with a good protocol. When your application and your code that you're writing is constantly redundant, a lot of redundancies in your code, you know you're working with a good specification. Now the evaluation is a little bit different. We're still looking for 0 for the function call itself, but now you want an 18 APDU length. I mentioned previously 16 bytes of data and a 2-byte response come back for this particular command. And it makes sense. We want the 16 bytes of data from block 1. We also want the 2-byte response. So we look at the length. If we have 90 hex, we have 90 hex and 0. We think, okay, well the read worked. We got 18 bytes. It's the right length. The status bytes indicate success. Now we're going to take a look at the data. We know what the data we wrote in. We're going to compare that to data that came back. As good responsible developers, we want to make sure that we get back the data we wanted. If those two arrays match, we know that the data that we wanted encoded in block 1 is truly there. Now we're going to close the connection. In this case, we're done with the card. We're going to close out the connection. Two things we have to do. We have to hand back the handle, and we have to tell PCSC what state we want the card to be in. In this case, I want the card to power down. I don't have any more need for that card, so I'm powering it down. The other option would be to reset the card. If I was going to continue working with the card, I might close it and open a fresh connection and have the card in a reset state. So we return the handle to the reader. And the final thing is to return the handle to the PCSC library. Returning that back on Microsoft, we no longer need access to their DLL. So at this point, we've gone through, we've loaded a card, we've loaded a key, we've authenticated the key, we've written data into the block, and we've read data back. The other thing I should mention, two things I want you to understand. All this PCSC code you notice here, I never talked about the ZXP-3, 7, or 8. That's because the nature of the reader being wired directly to the USB port and being able to talk to the reader directly. If I write this code for a MyFair 1K card for the ZXP-3, I take this code and I use it identically for 7 and 8. Doesn't matter which one of the ZXP-Series card printers I use, this code is going to work across all 3 printers. You also notice, hopefully you saw that we kept building command APDUs and evaluating response APDUs. Very good protocol, very simple, straightforward protocol for PCSC. It's actually not that difficult to work with them. It's a very consistent protocol, and then the interfacing between the print, the way the smart card reader has been wired into the printer, very consistent there as well. Zebra did a really nice job in following that same PCSC compliance implementation. One way of doing something, regardless of the smart card, one way of working with the smart card in the reader, regardless of the actual model of the printer, 7, 8, and 3. And all of this code would be called after the printer already positioned the card for encoding. I want to remind you, I mentioned that the card has to be positioned first, and that's the only responsibility the card printer has for encoding. With that, I'll move on to our references. Microsoft Windows has a wealth of information on their PCSC compliance. Simply go to MSDN, do a search on WinS-Card or S-Card Transmit. You can also look up the SDK and the driver, the device driver kit. There's very good information on that. PCSC Workgroup, they're the ones who came up with this protocol. A lot of good information there, some nice white papers, some sample code. I didn't talk about the Java world. In Java, you don't access PCSC directly. There's a SmartCard I/O library that Oracle gives you. It's a framework that's wrapped around PCSC. It's very powerful. I used it about 4 years ago. I haven't touched it in about 3. Very good. They have excellent documentation, a lot of sample code for Java out there, and some good white papers as well. Code projects. I like this particular website. I pull down code all the time. There are some very good articles on smart card use in the .NET world, and there are two developers that actually put .NET frameworks out there, similar to the Oracle framework. they put .NET frameworks out there. If you want to take a look at those, I haven't used them, but they look very powerful. SmartCard has what I call a simplified documentation. If you just want to distill down the basics of PCSC, get away from all the theory and the ISO specs and whatnot, and just understand the basics, they have an excellent set of documentation out there, and they actually are a competitor to the current SmartCard reader that's in the Zebra printer. I've used all these references. I highly recommend them. There's a wealth of information for PCSC on the internet. You should not have any trouble finding any documentation in any of the languages you work with. With that, I am now at the questions and answers point. At this point, I'd like to hopefully open up the floor to any questions you may have. I'll do my best to answer them. Anything you want to discuss, I know some of you that are in attendance know quite a bit about PCSC. If there's anything that you think I missed and should have covered, let's talk about that now. I'm going to open the floor now. Dan, if you wouldn't mind opening the floor to discussion and questions.
Sure. Thank you very much, Al. This has been great. Some really good information here. And as a reminder for everyone, we have this session recorded, and we also